well. So let us continue our lecture. Well, what we learned so far? We start talking about iterated integrals. Iterated integrals. Well, we said that in elementary calculus, we learned how to deal with just a simple integral. A simple integral had different meanings in different branches of science. One of them was finding the area below a function. Finding the area. In other cases, in application of integrals, we could see that, well, the simple integral of function f, it might be related to, for example, calculating the mass or finding the balancing point, the center, and many more applications. So when we are dealing with integrals, it doesn't always mean the area. It might have a different concept, or it targets something absolutely differently. But since it's easier for us to imagine the area, to imagine the volume, we keep talking about the area and volume. But again, it's not always about area and volume. So we said that, okay, here we had, for example, x-axis and then y-axis, and suppose you have a positive function, it means that the function is above x-axis, your y is positive. So here you have your function, y equals to f of x. And then we said that, okay, suppose we want to find the area below the graph between A and B. To find this area, a guy named Riemann came up with some solutions. He said, well, we can divide the x-axis into smaller sub-intervals and then find each of these lengths, then multiply that length by this measurement, which stops at y equals to f of x, calculate each one of these small areas, add them all together to find an approximation for this area below the graph. And eventually, they came up with the idea of using the limit and convert this Riemann sum into exact value using the ugly S integral. So here you have f of x, d of x, x ranges between a to b. It means that if we start walking on x-axis, here we start at this point, a, and we stop at this point, which is b. Our axis changes between a and b, and here you have heights. These heights, they are dependent on this function. As I start walking from a to b, my y value starts ranging from 0 to this top at y equal to f of x. Then we said that, okay, we know everything about taking the integral. Now, what if we are talking about space? Like what? Like if I'm interested in constructing a building, and then I'm interested, for example, in calculating the volume of that building. Double integral. Again, for simplicity, we are using the volume. We saw that double integrals have different meanings in different contexts. So one of them is called finding the volume. It might be finding the mass. It might be finding, for example, the flow. It might be finding the, for example, center of 3D object, and finding, for example, the density function. and more applications. Again, since it's easier for us to imagine area and volume, we keep talking about area and volume. And we said that suppose you have a building, you have a base for that building. This is the base for your building. And then you have, for example, your client is asking for a specific type of ceiling. That ceiling of the building can be a ceiling like this, or it can be tilted like this, or it might have different forms, different surfaces. That ceiling might be like this in general. So how do we maximize or minimize the volume? How do we actually find the volume then talking about the maximizing or minimizing the volume? Since this guy, the surface or the ceiling is Z equals to F of X and Y, and this is the base of the building that you're constructing, everything depends on the base and the height. We need to find the base and multiply that by the height, add them all together to find the total volume of this building. So what do we introduce? The double Riemann sum. And remember that then we are taking the limit, then these small volumes are getting smaller and smaller. Introduce the limit, and then this limit gives us double integral. So the exact volume is equal to the double integral of the ceiling, the height, as we are moving from one point to another point on x-axis, on y-axis. Well, now I expect you to ask, what if I want to bound my z value between two different functions? So here's the question. Question says, what if z itself is bounded between two functions, like h of x and y and g of x and y? So if we look at this guy, it says, hey, my z is bounded between 0 to z equals to f of x and y. Remember that our region is in xy plane. In xy plane, z is always 0. Now we are saying that, hey, what if my z is not bounded by 0? My z is bounded by another function. How do I calculate the volume or mass, flow, center, density, and so on? Here we're going to introduce triple integral. We're going to say that, hey, now that we have x and y, we're going to add another integral related to z. So here we're going to use dv, the element of integration for x, y, and z, and we're saying that, hey, our z is bounded by below by h and above by g. Very well. Give us some examples. Sure, let's go over some examples together. Suppose the question says, well, find the volume example find the volume bounded by this region. The region, suppose the region is defined this way. You have, for example, a box equals to the set of all ordered pairs like x, comma y, comma z, such that x is bounded between 0 and 1, and my y is bounded between -1 and 2. I'll just make it a little bit nicer, -1 and 2. And also, I have z bounded between, let's see, 0 and 3. What's the visualization? What is this guy talking about? This guy says, well, I have my x, I have my y, I have my z. Okay, my x is bounded between 0 and 1. Okay, let's make one a little bit here, further here, more measurements. This is my x is bounded between 0 and 1. And then my y is bounded between -1 and 2. So -1 and 2, this is my y. And then what else do I have? Let's just make it to 0 to 1, 0 to 2. Visualization is a little bit easier. Then z is bounded between 0 and 3. 1, 2, and 3. Okay, so here we have this guy, this object here, which is a box. Okay. So the question is actually asking us, what is the volume of this box? What is the volume of this box? I learned it before when I was in, I don't know, school. So the measurement is 1. The measurement is 2. The measurement is 3. 2 times 1 times 3 is 6. 6 unit to the 3rd power. This is the volume of this box. Now we are in multivariable calculus class. We're interested in using the technique that we just learned to calculate this volume and check to see if this volume is actually 6 or not. Okay. Since we are in multivariable calculus class, let us use, now that we have 3 variables, triple integrals. So it's very similar to what we learned in double integrals. As you can see, all of these boundaries are fixed numbers. What's the meaning of that? It means that the order of integration is not important for us. So since all boundaries are fixed numbers, the order of integration is not important. What's the meaning of that? It means that triple integral dx dy dz is the same as triple integral dy dx dz, the same as triple integral dz dx dy, and the rest of them. It doesn't matter if you take the integral with respect to x first, then with respect to y, then with respect to z, or take the inner integral with respect to y, then with respect to x, then with respect to z. It gives you the exact same value. Okay. Let us use dx, dy, dz, and calculate. So we're going to calculate the outer integral with respect to z, inner integral with respect to y, and the most inner part with respect to x. So we're going to have dx, dy, and dz. X ranges between 0 and 1. Y ranges between 0 and 2. And z ranges between 0 and 3. Okay, very well. So my most inner integral is an integral with respect to x. The integral of dx is x. X is bounded between 0 and 1. Then we are taking the integral with respect to z, then with respect to y, and then dy dz. This is a definite integral. 1 minus 0 is just 1. So this integral now becomes 0 to 3, 1 dy dz. Okay, here, let's write down the integral for y, 0 to 2, 0 to 3. Again, now we are taking the integral with respect to y, which is y bounded between 0 and 2. 2 minus 0 is 2. So this guy becomes integral 0 to 3, 2 times dz. Well, 2 is just a coefficient. 2 integral 0 to 3 dz is 2 times 3, which is 6. You get the exact same result. These two results are the same. Both of them are given as the triple integral of 3 variables. So think about it this way. If you want to generalize the idea, if you have 4 different variables, you're going to define an iterated integral with 4 integrals. If you have 5 different variables, you're going to generalize the idea to iterated integrals with 5 integrals, and so on. So now I expect you to ask, what if I have a whole different new function and I have my boundaries for my x, y, and z? So I have this box, and at the same time, I have an object, like 4-dimensional object, and that 4-dimensional object has an intersection with this 3-dimensional object. I'm interested in calculating the volume bounded by that 4-dimensional object and this 3-dimensional object. So question says, find the volume bounded by this 3-dimensional object and this 4-dimensional object